All right, so I had a question if I could kind of clarify this statement here. A statement during exercise, afterload is minimized due to arterial dilation, which makes it easier for the heart to pump a large volume of blood. So the first thing that I want to address is essentially what happens to blood pressure during exercise. We didn't talk about it directly here, but we talk about it later on in the lecture. So during dynamic exercise, we have our diastolic blood pressure, as seen here, stays relatively flat. However, our systolic blood pressure, 120 at rest, increases up to, let's say, I don't know, about 200 or so. Right, so if we then look at what our mean arterial pressure is, which is our average kind of blood pressure, during that we see an increase in mean arterial pressure. This increase is primarily due to the increase in systolic blood pressure, since obviously it can't be diastolic since that stays completely flat. All right, so I will say that yes, we do have an increase in blood pressure. However, we don't have these massive increases that ultimately get so high that we can't generate enough force in the heart in order to create a true barrier to ejection, such that no blood exits the heart. So as you might guess, that seems relatively obvious, right? So blood pressure, while it goes up, yes, we don't have these massive increases that prevents cardiac output from being ejected from the heart. So how does that work? So I've made another little PowerPoint with some terribly cheesy drawings in them. So let's take a look. So if we take a look at my drawing here, so here's our heart. Here we then have our arteries here that's pumping blood, and as you can imagine, that as we exercise, the increase sorry, trying to work on this. So as we exercise, we get an increase in cardiac output, right? So that cardiac output ultimately is going to mean that we're going to increase blood flow being pumped through the artery. As we learned, if you increase the flow, then you increase the pressure, right? So that's the same idea. If we think of this artery as a water hose hooked up to the water fountain on the side of the house, if we turn up the water, increase the amount of water going through it, then of course the pressure in that artery is going to be greater. So if we then look at the kind of normal route, what happens is we have blood flow through our arteries that then go into its resistance vesicles, the arterioles, which then feed into capillaries and provide our skeletal muscle with blood. Right? So as we start to increase flow, we get this, in theory, would get this huge increase in pressure. However, that's not the case. The reason that that's not the case is because only about between 60 and 80% of arterioles are actually open during rest. As we exercise, the metabolic demand of the skeletal muscle goes up. It uses autoregulation then to increase the number of arterioles that are open. So if we kind of see here, we start to add arterioles, and ultimately what we can do is then decrease ultimately the resistance to this by increasing the number of arterioles that are open. Therefore, we minimize the increase in blood pressure or in mean arterial pressure by having more of these vessels open, and in theory, although not directly changing kind of the size of the circulatory system, we do kind of change the amount of arteries that we can, so we can think about it that way if we think back to some of the other figures. So again, as we increase cardiac output, we increase the amount of blood flowing. Normally that would increase blood pressure and potentially have a massive increase in blood pressure if we didn't have these increase in the number of arterioles that are open to kind of dampen that huge increase in mean arterial pressure. And as we know, mean arterial pressure is equal to end diastolic volume, is equal to afterload. So we ultimately minimize afterload in muscle during exercise. So I hope that helps.